Alright, so today I'm going to be explaining this important paper with the title GraLSP, Graph Neural Networks with Local Structural Patterns. This AAAI paper in 2020. It is not until recently that graph neural networks are adopted to perform graph representation learning, among which those based on the aggregation of features within the neighborhood of a node achieved great success. However, despite such achievements, GNNs illustrate defects in identifying some common structural patterns, which unfortunately play significant roles in various network phenomena. So we propose this model, a GNN framework which explicitly incorporates local structural patterns into neighborhood aggregation through random anonymous walks. Specifically, we capture local graph structures via random anonymous walks, powerful and flexible tools that represent structural patterns. The walks are then fed into feature aggregation, where we designed various mechanisms to address the impact of structural features, including adaptive receptive radius, attention, and amplification. We design objectives that capture similarities between structures and are optimized jointly with node proximity objectives. With the adequate leverage of structural patterns, our model is able to outperform competitive counterparts. So this is a computational tree of a triadic closure graph. We take the triadic closures, patterns, characteristics of strong ties and social networks as examples. We showed the computation tree. The only difference the triadic closure makes is the existence of first-order neighbors, which are green nodes, on the second layer of the tree, whose impact tends to diminish as their neighborhood expands. It thus concluded that based on neighborhood aggregation, GNNs can in some cases fail to generate distinctive embedding for structural patterns that are topologically similar but carry widely different semantics. So how can we enable GNNs to more adequately capture and leverage multi-scale structural and node features? So the use is anonymous random walks, which I have also used anonymous random walks for my paper GSAT, Graph Structure Attention Network, that I generalize graph attention networks to include structural information as well. So like this paper, similar to this paper, everyone uses anonymous random walks because they capture the structural information very well. Asynchronous walks are projected, so we sampled random anonymous walks around it. Anonymous walks are projected to vectors which are then aggregated along a structurally aware neighborhood via attention and amplification. So here we calculate walk proximity loss and then node proximity loss. Then we add them, which is the total loss. You see, these local structures are captured very well by these anonymous walks. We compute empirical distribution of their underlying anonymous walks like this. We don't know the distribution, but we can approximate that distribution by this empirical distribution. So then we take the mean empirical distribution over the whole graph. Denoting anonymous walks as statistics is insufficient, as walks represent structural patterns with varying similarities to each other. For example, we intuitively believe that this sequence is highly similar to this sequence, as they both indicate an underlying triad. But is this similar to this, as no triads are indicated? So we would like to capture properties of varying walk sequences. We represent each anonymous walk as a vector through an embedding table lookup. So we introduce how we aggregate structures along with node-level features. We focus on how to aggregate node features under the impact of their local structural patterns instead of plainly aggregating them together using aggregation. So we design our aggregation like this. And W is just a walk starting from V sub I. WP denotes the piece node of walk W. While each random walk can be seen as a receptive path, properties of the walk imply different radius of reception. If a walk visits many distinct nodes, it may expand to nodes far away which may not exert impact on the central node. On the other hand, a walk visiting few distinct nodes indicates an underlying cluster of nodes which are all close to the central node. And then we introduce this attention module to model varying importance of neighbors. Also, they use this amplification module for channel-wise amplification or gate to model selective aggregation of node features. So we design our walk proximity as follows, such that it has these constraints, such that highly coappearing walks are mapped with similar vectors. By constraining walk vectors in this way, we are endowing walk vectors with semantics which can interpret similarities such that our operations of incorporation walk vectors into aggregation are sound. So as I said, we just summed these node loss and the walk loss. They did it for CycleCR dataset, Cora dataset, and other datasets that you see the number of vertices and edges in these vertices and the feature dimensions, and the number of labels in each of these graphs. This is a visualization on an artificial graph, where black dots denotes nodes surrounded by closed triads and white ones denote those by open triads. And this is results for link prediction on different tasks. You see how structure can improve their performance.